Hello, let's talk about weak acid equilibria and calculating the pH of weak acids. Weak acids are acids that ionize only partially, so the acids will mostly stay in their molecular form. These are usually molecular compounds, and then will ionize in water, but only to a small extent. Let's look at some examples of strong acids. We have seen things like HCl is a strong acid, and likewise nitric acid, so hydrochloric nitric acid, HNO3, or things like sulfuric acid are strong acids, H2SO4, sulfuric acid. So those will, if we put 1 mole of these substances in water, they will form 1 mole or 1 molar solution of that acid. So we end up with 100% ionization. So end up with H plus Cl minus, and so this reaction proceeds 100%, and we saw a similar example in class. Weak acids, however, these are molecular compounds that then react with water to form H3O plus, or in the case of bases, OH minus. So they form H3O plus, or in the case of bases, and we can also look at this weak acid and base equilibria right here, or OH minus. So a typical weak acid is acetic acid, CH3, COOH, and this COOH group is really structured as carbon with a double bond to an oxygen right here, and another oxygen and a hydrogen, and then anything here on this side of the carbon we can represent with R. That means that any other carbon chain can hang off of here. So we end up with a variety of these carboxylic or organic acids. And then the acidic proton right here is this one, and that is the one that is then donated away and causes the substance to be an acid. Carbonic acid is also a weak acid. And that has the formula H2CO3. And there are a variety of other weak acids that are not organic compounds, but still molecular compounds. So the general ionization form of a weak acid can be represented by this equation. And so the equation would be HA for the acid. So H indicates the ionizable proton in the molecule. So say, for example, this proton in acetic acid, or one of these protons in the carbonic acid. A for the conjugate base, so in this case it's still bound to the acid, plus H2O, and then that makes an equilibrium to form H3O plus A minus. And all these species are in water. So we can then represent the equilibrium of this acid reaction right here with the acid equilibrium constant, that is abbreviated K sub A, for A for acid. And again, this is written as the products over the reactants. So we have H3O plus multiplied by the concentration of the conjugate base, and then the concentration of the acid in water. Again, we have our acid, water as our base, the hydronium ion as our conjugate acid, and the conjugate base here represented as A minus. And this acid ionization constant we can just usually look up in a table. As Ka increases, that means that the acid is a stronger acid. So the bigger K is, the stronger the acid is. Because that means then we have more of these acidic products right here. We can then set up the equation here where we set the Ka equal x squared over 0.150 minus x, which are the variables that represent the acetate ion, the hydronium ion, and in this case the acetic acid. And this again gives us a quadratic. However, we don't need to solve for a quadratic because we can assume right here that this is a small, that this change right here is very, very small. So this, so the ionization is very small. We can make an assumption that this is small and we can drop it. Drop this x in the denominator. So then we can write the equation as such: 1.80 times 10 to the minus 5 equals x squared over 0.150, and then we can solve for x, and then we can just solve for x. Once we find what x squared is, we multiply 0.150 times 1.8 times 10 to the minus 5 to get that out of the denominator, and take the square root, and that'll give us x, and x equals 1.643 times 10 to the minus 3 and this is now in moles per liter, and that equals the concentration of H3O+. And so then the pH of the solution right here is the negative log of the concentration of H3O+, and it is 2.78. Now, whenever we do this assumption right here where we want to drop that x in the denominator in the quadratic, we need to assume that this x is small. And so we need to verify that. We can then calculate the percent ionization from the amount, the x value, which represents the concentration of H3O+ or the acetate ion, divided by the initial concentration of the acid, which in this case was 0.150 molar. And here, the x that we just calculated, the concentration of H3O+, 1.643 times 10 to the minus 3, divided by 0.150. Both of these have units of moles per liter, so they cancel out, times 100. So we end up with 1.095%, or roughly rounded to 1.1%. And we can use this shortcut if less than 5% is ionized. So if this number were to be larger than 5%, we would still need to do the quadratic. So this means that about 1% of the acetic acid has converted to hydronium and acetate ions. So let's represent that graphically here in the balanced equation. So that means really only about 1% of the reaction has proceeded the way it's written. It is 99% acetic acid in its molecular unionized form. Only 1% of the acetic acid has been converted into the acetate ion and the hydronium ion. Contrast that with a strong acid, where this is a 100% reaction, and the pH of 0.150 molar hydrochloric acid is below 1, versus the pH that we calculated here is 2.78. So the pH is a lot higher with the acetic acid. We can compare the results we would have gotten if we'd calculated this problem with and solved it with a quadratic. Let's do it. So instead of dropping this x right here, let's leave that in and solve for the quadratic. So if I rearrange that equation on the preceding page, I obtain this quadratic, x squared plus 1.8 times 10 to the minus 5x minus 2.7 times 10 to the minus 6 equals 0. And if I solve this in a quadratic equation solving tool, I end up with the first x equals 0.001634. And the second x would be a negative number, so this would not be plausible. Therefore, the concentration of H3O+ is represented by that x that is a valid solution of this quadratic, which is 0.001634 molar. And that is just a small difference from the x we calculated with this nifty shortcut that we did here earlier. So it looks like just the two last digits here are transposed. And that gives us the answer of 2.79. So only a small difference from what we calculated in the previous step by taking that shortcut. So not a very meaningful difference. Again, if you do make this assumption right here of dropping this x in the denominator, make sure to check that the assumption is valid. And if it is not valid, then you need to use the quadratic. Thanks for watching. I hope to see you again in class soon.